The purpose of a motor is to convert electrical energy into mechanical energy. Shown here is a simple electric motor such as you might find in a power tool. As we start this problem, we're going to make a few assumptions about the motor. First, we're going to assume that the mechanical output as measured at the shaft of the motor is 1 horsepower. Second, we're going to assume that the motor is 85% efficient in converting electrical power to mechanical power. Now, since it's not 100% efficient, there will be some waste heat given off. And you know this to be true, especially if you've ever touched a working motor, you'll know that the case is hot to the touch. Since we're given the output power and we know the efficiency, we can calculate the input power. Now you'll recall that efficiency is defined as useful power out divided by the power in. Let's do ourselves a quick favor and convert everything to watts. Now we know that 1 mechanical horsepower is equal to 740 watts. So knowing that, we can plug everything into our efficiency equation. So efficiency is 0.85, the power output is 1 horsepower, which we said is 746 watts, and we're looking for power in. And when you solve that, power in is approximately equal to 880 watts. I'm going to move these numbers up to the middle of the screen. So power output, we said, was 1 horsepower, which is also equal to 746 watts electrical. And we said the power input was 880 watts. You can see there's a big difference between these two numbers. In fact, we can calculate it here. 880 minus 746 means we've lost approximately 130 watts. And where did it go? Well, being as I'm doing it in red, I think you already know, that extra power is simply lost as waste heat. To help explain this situation, I'm going to include a power flow diagram. So here we have power in on the left and power out on the right. And you'll see that they're not the same size because we've lost power along the way. A large part of it is lost to heat. And what happens is the current flows through all the coils inside the motor. They get hot, and so we lose power to heat. There's also a little bit of friction in the motor because there are moving parts. And here's an interesting one. It's called windage. Now we know the motor gets hot, and we need a way of cooling that motor. So what most designers do is they install a fan, and that fan is driven by the mechanical shaft, and it blows air over the windings of the motor. Well, that fan doesn't come free. It takes a certain amount of power to run that fan, and so we have a windage loss. And if you work these numbers, forgiving the rounding errors I've made, you'll see that the power in is equal to the power lost as heat plus the useful power out. So 880 watts is approximately equal to 130 plus 746. There's one last concept I want to include in this video because I think it fits very nicely with our discussion, and that is the concept of efficiency and how it varies as a function of the load that's placed on the motor. So here we have a graph showing horsepower on the horizontal and efficiency on the vertical. And a typical motor might have a curve something like this. Most motors have the best efficiency when they're operating at rated power. In this particular case, we have a 1 horsepower motor, and it has the best efficiency, which is about 85% at this rating. And you'll see as you drop off in power, as we move to the left, the efficiency drops. In fact, it drops all the way to 0 when there's no load on the motor. And you can imagine in this situation, the motor is turning and the fan is blowing all that air, but the motor has no useful power output. Likewise, if you overload the motor, you can start to see that the efficiency drops off as well.